Hi everyone, my name is Juliana Noronha and today I'll be presenting the status of my Data 675 course project, which I'm calling the San Francisco Traffic Danger Index. This project asks the following question. Are streets we think of as dangerous in San Francisco actually the most dangerous ones, or are we just looking at the busiest streets? In this presentation, I will walk you through the problem I'm trying to solve, why I think it matters, the two data sets I'm working with, and the most important things I've learned so far. So let's get into it. I'll start with the scope. First, what is this project? I'm building an exposure normalized traffic danger index for San Francisco intersections. That phrase, quote, exposure normalized, is really the heart of this whole project, and I'll unpack it on the next slide, but the short version is I want a danger score that accounts for how much traffic an intersection actually carries. How will this be accomplished? I will divide injury crash counts by measured traffic volume to produce a rate, crashes per 1,000 daily vehicles. That's the exposure normalized metric. Instead of asking how many crashes happened here, we're asking how many crashes happened here relative to how many opportunities there were for a crash to happen. And finally, what will the output be? Two things. First, a geocoded danger map showing which intersections score highest after controlling for volume. And second, two predictive ML models, one that classifies intersections as high risk or not, and one that predicts the continuous danger score as a function of the intersection attributes. That second piece is going to give us the ability to answer the question, which features of an intersection predict excess risk? So that could include road class, like is it arterial or residential, the mix of road users, and the speed of traffic. Now, let's dive deeper into the concept of exposure normalized traffic danger, which is quite a phrase to unpack. The issue is this. When you look at a city's crash map, what you see is a heat map of where crashes happen most often. And predictably, the hottest spots are the busiest intersections like downtown corridors, major transit hubs, etc. In San Francisco, that's Market Street, Van Ness, Mission. Those are the places that show up as bright red. But what that map is showing you mostly is just where most of the cars are. More cars are almost always meaning more crashes, and this map doesn't do a very good job of distinguishing between these two situations. In the first situation, an intersection has lots of crashes because it's incredibly busy, and the rate per vehicle is actually quite normal, what you would expect for such a high volume. In the second situation, an intersection has crashes at a rate that's much higher than you would expect given its traffic. Maybe that's because the sightlines are bad, or the signal timing is confusing, or the road geometry encourages drivers to speed. Those two situations call for completely different responses, but they look the same on a raw count map. And that second category, intersections that are dangerous because of something that's fixable, is exactly what I'm trying to find. Poor lighting, confusing road markings, inadequate signage, road geometry, all of these things can elevate crash risk independently of traffic volume. But they're invisible in a raw crash count analysis because they're swamped by areas with high traffic volume. So the solution I'm proposing is to first control for volume so that what remains is the residual risk that can't be explained by how busy an intersection is. And the research question this leads to is which intersection characteristics predict elevated injury risk after controlling for traffic volume. So why did I choose this project specifically? Two reasons. First is very selfish. I live in San Francisco. I walk, bike, take transit through these intersections every day. And when I cross an unfamiliar intersection or I'm in a new part of the city, I really have no way of knowing whether it's genuinely dangerous or just busy. The public-facing tools available, like a crash map that is released that shows the raw crash counts, they all reflect these raw counts. The second reason is policy. So we're all aware that cities have limited budgets in general, but traffic safety infrastructure is one of those things. A protected bike lane installation, crosswalk redesign, these are things that cost money, and there are hundreds of intersections in a city competing for that money. If the prioritization is based on raw crash counts, the dollars are always going to flow towards already busy downtown intersections because that's what the data seems to say. But those may not be the intersections where intervention would save the most lives per dollar spent. So my goal with this exposure normalized danger index is to give planners a more defensible basis for those decisions for those lower volume areas. The people who would benefit most from this project fall into three groups. City planners who would get a better analytical tool, cyclists and pedestrians obviously who are disproportionately injured in these crashes, and so they stand to gain the most from interventions directed at dangerous locations. And everyday residents who deserves a map that reflects actual danger and not just the traffic density. I want to briefly mention the scholarly foundation here. Yanis et al., it's linked at the bottom of the slide, did a literature review in 2017 of road traffic accident prediction models, and they consistently find that traffic volume is the dominant explanatory variable in crash frequency models across dozens of studies worldwide. And so that finding informs the logic of this project. If volume drives the most variance in crash counts, then any analysis that doesn't account for it is essentially just remeasuring the volume. Now I'm going to start walking through the data sets. The primary data set I'm working with is the San Francisco traffic crashes resulting in injury data set published by DataSF by municipal agencies. It contains 65,282 crash records with 58 columns from 2005 to the present, though for this project I'll restrict the analysis to 2014 through 2022 due to limitations on the second data set, which I'll cover shortly. So each record includes the latitude and longitude of the crash, the exact date of time, injury counts broken out by killed and injured, party types, so that's whether each party involved was a driver, a cyclist, or a pedestrian, the road surface condition, lighting conditions, weather, the type of collision, the movement of each party preceding the crash, so where they're coming from. There's also an intersection node key, which links each crash to the nearest intersection in the city's network. And that field will be the primary join key for connecting crash records to traffic count locations. And we'll talk about that on the next slide. On data quality, there are a few issues worth flagging. The most significant is that there are about 2,000 records, or about 3% of the data set, that have a positive longitude value instead of a negative one. San Francisco is roughly at negative 122 degrees longitude. So a positive value places those records in Asia. So that's clearly a data entry error where the minus sign was dropped, and those records need to be corrected. There are also about 200 records with missing coordinates entirely, so those will have to be dropped, unfortunately. Control device field, which would tell us whether the traffic signal or stop sign was functioning, is null for a third of the records, which limits its usefulness as a predictor variable. Onto the second data set. This is the SF-MTA intersection traffic counts data set, which is available through their data portal. This data set contains counts of traffic across different modes of transportation at hundreds of intersections in San Francisco. There are about 1,200 intersection records across 126 columns, and it covers count dates from 2014 through 2022, which is why that window becomes the analysis window for that whole project. This data set is much more complex than the crash data in terms of its structure. Beyond simple vehicle counts, there's also the number of vehicles approaching an intersection from the north, south, east, and west, the number departing in each direction, broken out by time period. So these are categorical: morning, afternoon, midday, and weekend. There's even a special category for post-ball game traffic near Oracle Park. It also includes separate counts for bicycles and pedestrians in either direction, as well as the average speed, the 85th percentile speed, which is a standard traffic engineering metric, which communicates the prevailing traffic speed. The critical join challenge here is that this dataset identifies locations by street name and cross street, so that's primary ST and cross ST, rather than by geographic coordinates. That means I can't directly match it to crash records, which are geocoded. So a necessary data prep step is going to be geocoding those street name intersections to lat and lon, and then I'll be able to join to the nearest coordinates on the crash records. Additionally, these counts were not measured daily between 2014 and 2022. This data set represents a small sample of recorded traffic counts, so I will also have to join to the nearest date and time of day. There are also some significant data quality and coverage limitations worth being upfront about. The volume ADT field, which is average daily traffic, would be a really convenient denominator for this project, but it is almost completely null. It only exists for about 31 of the 1,200 records, so I'll probably need to construct some kind of proxy measurement for that. Many of the other columns are even sparser. The midday, weekend, and ball game counts are missing from 95 to 100% of the records, and so I will likely drop these during the modeling stage. Roadway class, which classifies intersections as arterial, residential, and so on, is missing for about 65% of records, but that is present in the other data set, so we'll see if we have to drop that. Finally, the danger index will only be computable for intersections that appear in both data sets. So we can't do it for intersections that don't have a traffic volume, and we can't generate a danger score for those. So I will close with the 3 most important things I've learned from the work so far. The first lesson is that dataset provenance matters more than size. When I started this project, I looked at Kaggle first because it has a huge volume of datasets and it's really easy to search, but I kept running into datasets with no documentation about how they were collected, who was maintaining them, when they were last updated. One that looked very attractive to me, a dataset on data center resource usage, had no methodology documentation at all, and I couldn't determine whether it was real data or synthetically generated. I even messaged the guy who uploaded the dataset to ask for the code that generated it, and he sent me a very short code file that had to do with breast cancer. So that told me everything I needed to know about the quality of that dataset. I ended up turning to San Francisco's open data portal, where datasets are maintained by city agencies with a lot of documentation on how the data is collected, how frequently it gets updated, and there's a lot of accountability there. These datasets are more work to prepare, but I trust them. So the second lesson is that the scope has to match the available resources. Early on, I considered using the Google Maps API as a proxy for traffic volume, which would have had complete coverage over that crash dataset time period, temporally and geographically. But querying the API at the scale that I need for this citywide historical analysis would have cost some real money, and this project has no budget, obviously. Also, the Google Maps API uses phone signals as a proxy for traffic volume, which doesn't specifically account for pedestrians, bicyclists, and drivers. So all of these factors pushed me towards the SFMTA counts data, which is free and has that added complexity for the preparation work, but recognizing that constraint early and making the practical choice was a useful exercise in project planning. The third lesson is that exploratory analysis is very foundational. It's sort of easy to treat descriptive stats as something you do very quickly before getting to the real work of modeling, but that's the wrong framing. You make so many decisions during this exploratory phase, understanding which columns are usable, which records need to be filtered out or corrected, how to construct your additional features from incomplete data. All of those decisions propagate through every step, and it's a really critical part of the analysis pipeline and allows you to build an intuition around the data. So that's where the project stands. I have 2 well-documented data sets, a clear research question, plans for the join and the calculation for exposure normalization, and some models scoped out. So the next phase will be executing the data prep and beginning to build out these models. I'm happy to take any questions or feedback from the group. Thank you so much.